Okay, welcome to the third questions in period of simple harmonic motion. Okay, a 0.6 kilogram mass at the end of a spring vibrates 3 times per second and with an amplitude of 120 cm. What is its velocity when it is 100 cm from the maximum position? Okay, this is something we should take note. From the maximum position, not from the equilibrium position. Okay, be careful. Also determine the spring constant. Okay, so what we have is the mass. We have the mass. We have the amplitude. This is the amplitude, but in cm. Okay, he said vibrates 3 times per second. This is the frequency. 3 times per second is the frequency. And what is the velocity when 100 cm from maximum? Okay, never mind. So we have the mass already in SI unit kilogram. Frequency is 3 times per second, which is 3 times per second. Per second is hertz. Okay, 3 hertz lah. Yeah, 3 hertz frequency. Amplitude is 120 cm. Amplitude is 120 cm. So change to meter. Change to meter. It is 1.2 meter divided by 100. Be careful with the unit. Now, what is the velocity when it is 100 cm from the maximum position? Okay, this one is not equilibrium. This one does not come from equilibrium. Does not come from equilibrium. So this is a bit dangerous. He said from maximum, 100 cm from maximum. So we must determine where is the displacement first. Where's the position of this object? Okay, this is how I draw here already. This is the equilibrium, and this is the amplitude. Okay, the amplitude is actually the amplitude between the amplitude and equilibrium, it is 120 cm. Okay, 120 cm. So he say this object is 100 cm from maximum. That means 100 cm from maximum. So this 100 cm is not from equilibrium, but is from maximum. This 100 cm is from maximum, not from equilibrium. So this is not x. This is not x. 100 cm is not x. 100 cm is not x. It's 100 cm from the amplitude. It is 100 cm from amplitude. 100 cm from the maximum position means what? Means the amplitude. 100 cm from the amplitude. So our displacement from the equilibrium is actually only 120 minus 100, which is only 20 cm. It's only 20 cm from the equilibrium. So our x is actually 20 cm. Our displacement x is only 20 cm, which is also 0.2 meter from equilibrium. This one is from equilibrium. So be mindful that our x always from equilibrium, not from amplitude. Okay, our x is always from equilibrium. So it's 0.2 meter from equilibrium. So our x is not 100, but it's only 20 cm or 0.2 meter from equilibrium. Okay, so no matter what, we already found the x. So to find the velocity with given position, so we need to use to find this velocity, because we have the position, we need this velocity versus displacement formula. Okay, velocity versus displacement formula. Okay, so we need to use the velocity versus displacement formula, which is positive negative omega square root a square minus x square. Okay, so all right, so omega is 2 pi f3, so this is 6 pi. Okay, we have the frequency already, just put inside, so this is 6 pi. So let's put 6 pi there, and then amplitude is okay. Make sure cm convert to meter. So that's 1.2 square minus x. So be careful. Our x put 0.2 meter, not the 100 cm, which is 1 meter. So our x now is 0.2 meter. Okay. So what's our velocity? Our answer is positive negative 22.3 meter per second. Okay. So positive negative means it has at this position, okay, the velocity is equal to positive negative 22.3 meter per second at x equal to this positive 0.2 meter. That means at this position, the object can have two possibility of direction. Maybe at this position, the object is going up, positive velocity. Maybe the object is going down, negative velocity. So if given position, we cannot determine for sure what's the actual direction of velocity. It has two possibility. That's why we put positive negative sign. Okay. Only if you give a certain actual time, if you give time, then we can only have one direction of velocity. We can know for sure what's the direction of velocity if given time. If given displacement, we can there are two possibility of direction of velocity. Okay. Now, next, we got the velocity. Now, determine the spring constant. Determine the spring constant. So we just use the formula k equal to m omega square. K equal to m omega square. Do we have the mass? Yes, we have the mass 0.6. Okay. 0.6 kilogram. Okay, it's already in kilogram. The omega, yes, 6 pi. 6 pi. So our k is equal to 213.18 Newton per meter. That's our k. Okay, that's our spring constant. Or you want to use another formula, which is period equal to 2 pi square root m over k. You also can find the k. The period you take from omega equal to 2 pi over period. We already have the omega. Sorry, we already have the omega. So we can get a period. We get a period, we can use this formula to find the k. Okay? Or you just use k equal to m omega square. Same. Yeah, you want to use this formula, k equal to m omega square, or this period formula, you still get the same answer, 213.18 Newton per meter for spring constant. Okay, so that's all for these videos. Okay, see you again. Bye.